Hi, my name is Shania Navarro, and this is my lab report on the magnetic field of a dipole magnet. The goal of this lab was to investigate the magnetic field generated by a small bar magnet. I used a magnometer app to collect data and visualized the magnetic field using code. This experiment helped me understand how theoretical physics equations apply to real-world magnetic interactions. The purpose of this lab was to measure the magnetic field strength at various distances from a bar magnet, determine the distance dependence, and compare my real measurements to a model based on the magnetic dipole field equation. The fundamental physics principles involved were the magnetic dipole field equation, distance dependence, and the vector dipole field formula. This lab was based on the magnetic dipole field equation. The field strength follows a power law with distance generally decreasing because of the 1 over r cubed. The full vector form of the dipole field includes both direction and magnitude and is especially important when the observation point is not directly on or perpendicular to the dipole axis. For this experiment, I used a bar magnet, my smartphone with a magnometer app, and tape with meter stick measurements labeled on it to measure and align everything. I placed the phone flat, aligned it with Earth's magnetic field, and used the X component of the magnetic field for on-axis measurements. It was important to align the phone with the Earth's magnetic north so that the x-axis of the magnometer app corresponded to the direction perpendicular to Earth's field. I also identified the sensor location on my phone using the method described in the lab guide, so moving the phone to find where x and y components peaked or minimized. Before taking measurements, I aligned the phone until the x component of Earth's magnetic field was as close to zero as possible. This ensured the magnet's field would show up cleanly in the x direction with minimal interference from the Earth's field. In my area, Marietta, Georgia, the Earth's magnetic field is about 49 microteslas. When the magnometer was far from the magnet, the x component of the field was close to zero. As I moved the phone close to the magnet, the x component increased. This confirms that the magnet's influence gets stronger as distance decreases. So the correct statements are the x field is near zero, far away, and it increases as you move closer. I recorded field strengths. Graph to the right shows the natural log of bx against the natural log of distance and got a line with slope negative 2.526. This slope represents the experimental value of the distance exponent n. For the off-axis portion, I measured the field at positions perpendicular to the magnet's axis, and then I corrected the y component of the magnetic field by subtracting Earth's contribution. This is section 3.2 in the lab, which is just my work for computing the distance dependence first using the equation from the graph and then finally calculating the magnetic moment. Next, I created a computational model using GlowScript. I implemented the full dipole field vector equation which calculates the field based on the magnet's moment and the observation point. I used the magnetic moment I determined earlier from my data. This image shows my visualization of the magnetic field. Orange arrows represent field lines along the axis. The cyan show the perpendicular fields, and the magenta represents a field at 45 degrees. This helps me understand how the field behaves in 3D space. The value computed by my code was in the same range as my experimental value, showing that my model matched the physics result fairly well. In my model, I assumed the magnet was a perfect dipole and that the magnetic moment was constant. I also assumed no nearby magnetic interference and accurate alignment of the sensor. These assumptions helped simplify the model and kept it focused on the dipole interaction. If I hadn't aligned the phone to magnetic north, the Earth's magnetic field would have interfered with the X component readings. This would make the results inaccurate or inconsistent, and my plot of ln bx versus ln r wouldn't have produced a clean line. If I repeated this experiment using two identical magnets stuck end to end, the magnetic moment would double. Since the dipole field is directly proportional to the magnetic moment, I'd expect all of my measured field values to double while the distance dependence n would remain unchanged. Some sources of error include inaccurate alignment, nearby still objects, and misreading sensor location. Fluctuations in the environment or phone movement during measurements could also affect the results. Magnetic dipoles like this are found in magnetic sensors, electric motors, and even Earth's magnetic field. The concepts we studied in this lab relate to many engineering and physics systems, including MRI machines and compasses. In conclusion, I found that the magnetic field increases as I move the sensor closer to the magnet, and the field decreases with roughly the cubed of the distance. My coding model visualized the field in 3D and matched experimental values, confirming the accuracy of the dipole field equation. Thank you for watching my lab report on the magnetic field of a dipole.